Hello there, and welcome to the Sleep Well channel. I'm so glad you found your way here. Perhaps it's been a long day, filled with the noise and hurry of the world. Or maybe you're simply the kind of person who finds peace in looking up and wondering about the vast, silent spaces between the stars. Either way, this journey is for you. There is nothing you need to do now but rest. Let your body grow heavy, your breath find its own quiet rhythm, and your mind begin to soften like mist settling in a cool valley. Because tonight, we are not just stargazing, we are listening. We're tuning our attention to the deepest, most ancient sounds of the cosmos. Not sounds our ears can hear, but signals carried on light, on radio waves, and on the very fabric of space-time itself. These are the unexplained messages from deep space. Faint whispers, sudden shouts, and steady rhythms that have crossed billions of years to reach us, carrying questions we still cannot answer. Some of these signals may surprise you. Others may simply drift by like distant melodies at the edge of sleep. Each one is a reminder that the universe is not a silent, empty place, but a vast ocean of energy humming with stories we are only just beginning to hear. And just before we begin our gentle drift, if these calm explorations help you rest or give you a quiet way to end your day, consider gently tapping the like button and subscribing. It helps other sleepy souls find their way to this quiet corner of the world too. But for now, let your thoughts float. Let the darkness behind your eyes feel like the soft, endless canvas of space. And if you're ready, let us begin to listen. There was a signal once that arrived like a single perfect note in the middle of a silent symphony. It came in the summer of 1977, captured by a radio telescope in Ohio pointed toward the constellation Sagittarius. For 72 seconds, the telescope recorded a burst of radio waves so strong, so clear, and so perfectly tuned to a frequency that scientists had long suspected intelligent life might use, that it seemed impossible. It was a signal that stood out from the background noise of the cosmos like a human voice in a forest of wind and rustling leaves. When an astronomer named Jerry Eman discovered it in the beta days later, he was so stunned that he circled the reading on the printout and wrote a single word in the margin, "Wow." The name stuck. The wow signal was not just strong. It was narrow-focused and unlike any known natural phenomenon. It was exactly the kind of signal humanity had been searching for. And then just as suddenly as it had appeared, it was gone. In the decades since, astronomers have returned to that same patch of sky again and again, listening with ever more sensitive instruments. But they have found only silence. The signal has never repeated. It remains the most compelling candidate for an extraterrestrial message ever recorded. Yet, it is a message of just one word, a single, powerful burst that crossed unimaginable distances only to fall silent forever. It's a quiet reminder that the universe may be speaking, but its conversations are not always meant for us to overhear. And sometimes, the most profound messages are the ones that are only ever spoken once, leaving behind an echo of pure, unending wonder. Not all signals arrive with such a sudden shout. Some begin as a quiet, rhythmic pulse, so steady and so perfect that they seem impossible. In 1967, a young graduate student named Jocelyn Bell Burnell was scanning the sky with a new radio telescope. She noticed a strange repeating signal, a pulse that arrived with a precision no human clock could match every 1.337 seconds, again and again and again. It was so regular, so artificial seeming, that the research team half-jokingly nicknamed it LGM-1 for Little Green Men. For a time, they seriously considered the possibility that they had discovered a beacon from another civilization, a cosmic lighthouse sweeping its beam across the galaxy. It was a thought both thrilling and deeply unsettling. The signal was too fast to be a spinning star, too regular to be random noise. It felt for a moment like a greeting, but then she found another, and another, all pulsing with their own unique, unwavering rhythms. The truth turned out to be just as strange, if not more so. These were not alien signals, but pulsars, the collapsed spinning cores of massive stars that had long since died. These city-sized remnants of supernovae sweep beams of radiation across space, and when that beam crosses Earth, we hear a pulse. The discovery changed astronomy forever, but the initial mystery lingers. For a few quiet weeks, humanity stood at the edge of what felt like a monumental discovery, listening to a perfect cosmic heartbeat, and wondering with a sense of profound awe who might be on the other end. Even knowing the answer, the memory of that question still hangs in the silence between the pulses. While pulsars offer a steady rhythm, the universe also sends signals that are the complete opposite, sudden brilliant flashes of energy that last for less than the blink of an eye. They are called fast radio bursts, or FRBs. These are among the most powerful and mystifying events in the cosmos. In just a few milliseconds, a single FRB can release more energy than our sun produces in an entire day. They flare up from galaxies billions of light years away and then vanish without a trace. What could create such an incredible burst of power? For years, scientists had no idea. The signals were so brief and came from so far away that their source was a complete mystery. Some speculated they could be from colliding black holes, exploding stars, or even the engines of alien spacecraft. They were like cosmic lightning flashes without a storm, sudden shouts from across the universe. We now believe that at least some of these bursts come from magnetars, a special kind of neutron star with an unimaginably powerful magnetic field. But many FRBs remain unexplained. Some have been seen to repeat flashing intermittently from the same spot in the sky, while others are single, cataclysmic events that are never heard from again. Each burst that arrives is a piece of a puzzle, a fleeting message written in radio waves that tells us the universe is far more energetic and dynamic than we ever imagined. Even in what appears to be empty space, immense power can be unleashed in a silent, brilliant instant. Not all mysterious signals arrive as radio waves. Some are written in the subtle language of light. There is a star officially known as KIC 8462852, but better known as Tabby's star that flickers in a way that nothing else does. Most stars dim for predictable reasons. A planet passes in front, or the star itself pulsates. But Tabby's star dims erratically, unpredictably, and by a staggering amount. Sometimes its light dips by just a fraction, but at other times, it has been seen to lose up to 22% of its brightness. That is far too much to be a planet. A planet the size of Jupiter, passing in front of a star like this, would block only about 1% of its light. So, what could be casting such an enormous, irregular shadow? The observations have left astronomers baffled. Theories range from a swarm of comets to the shattered remnants of a planet, but one of the most intriguing, though highly speculative possibilities is that the dimming is caused by an alien megastructure, a vast swarm of solar collectors built by an advanced civilization to harness the star's energy. There is no direct evidence for this, and natural explanations are still being explored. But the mystery remains. The star continues its strange arrhythmic flickering, a signal not of sound, but of shadow. It's a quiet, unsettling dance of light and darkness playing out across hundreds of light years, reminding us that even a single, ordinary-looking star can hold a secret so profound it challenges everything we think we know about our place in the cosmos. While some stars send their signals in shadow, their light flickering like a nervous candle flame, others keep a rhythm so perfect, so precise, that they challenge our very understanding of time. From the quiet chaos of Tabby's star, we drift now into a realm of astonishing order, a place where the universe has built its own clocks. These are the pulsars, the cosmic heartbeats that echo in the radio silence. Some of them spin with a speed that defies imagination, rotating not once a day or once an hour, but hundreds of times every single second. These are the millisecond pulsars, and they are some of the most stable timekeepers in the known universe. Imagine a star, heavier than our sun, crushed by its own gravity into a sphere no wider than a city. Now, imagine that sphere spinning faster than a kitchen blender, a blur of matter so dense that a single teaspoon of it would weigh more than all of humanity combined. This is a millisecond pulsar. They are born from ancient slow-moving neutron stars that have a companion star orbiting nearby. Over millions of years, the neutron star's immense gravity pulls material from its companion, creating a spiraling disk of gas that falls onto its surface. This infalling matter acts like a celestial motor, spinning the dead star faster and faster until its rotation becomes a dizzying, relentless hum. What makes them so profound is their consistency. The best millisecond pulsars keep time more accurately than the most advanced atomic clocks on Earth. Their rhythm is a signal born from the perfect balance of gravity and motion, a pulse that has not wavered for millions of years. When astronomers listen to these signals, they are not just hearing the echo of a dead star. They are hearing a fundamental rhythm of the cosmos. It's a quiet, steady beat that can be used to test the laws of physics, to search for the faint murmurs of gravitational waves, and to navigate the vast distances of our galaxy. It is a signal that feels less like a natural phenomenon and more like a piece of perfect celestial machinery humming softly in the darkness, a testament to the order that can arise from even the most violent stellar death. In the deep quiet of space, these stars are keeping a time that is older and truer than our own. A constant, reassuring beat in the endless night. And yet, even this perfect order is sometimes broken. For all their astonishing stability, pulsars can sometimes do something that feels deeply, fundamentally wrong. They can glitch. A pulsar glitch is a sudden, tiny speed-up in its otherwise flawless rotation. Imagine a record player spinning a song with perfect rhythm for 1,000 years, and then in an instant it skips forward by a fraction of a beat before settling back into its steady pace. That is a glitch. These events are completely unpredictable, and happen in a fraction of a second. For a moment, the cosmic clock runs fast. Scientists believe these glitches are born from the strange exotic physics deep within the neutron star's core. The interior of a pulsar is thought to be a superfluid, a state of matter that flows without any friction at all. As the star's outer crust slowly spins down, the superfluid interior may continue to rotate at its original speed. Tension builds between these two layers until suddenly the superfluid transfers some of its rotational energy to the crust, causing the star to jerk forward. It is in effect a starquake, a tremor that shakes the very foundations of a dead star and sends a tiny, almost imperceptible shiver through its signal. To us listening from light years away, the glitch is a whisper in the data, a momentary flaw in a perfect rhythm. But it is a signal from a place we can never see, a world of superfluid matter and unimaginable pressures. It's a reminder that even in the most orderly systems in the universe, there is a hidden chaos, a tension that can build for centuries before releasing in a single silent instant. The glitch tells us that the heart of a star, even a dead one, is not still. It is a place of strange, deep physics where the rules of our world no longer apply, and where even time itself can be made to skip a beat. The mysteries of these cosmic beacons do not end with a skipped beat. Some pulsars send a signal that is even more puzzling, not because of its rhythm, but because of its absence. There are pulsars that seem to turn on and off. For days, weeks, or even years, they will pulse with their signature regularity, their radio beams sweeping across the sky like a faithful lighthouse. And then, without warning, they will simply go dark. The signal vanishes completely, as if a switch has been flipped somewhere across the galaxy. These are known as intermittent pulsars, and their behavior challenges our understanding of how these objects work. What could cause a star-sized radio transmitter to fall silent and then just as mysteriously begin broadcasting again? One theory is that the pulsar's magnetic field, the very engine that powers its radio beams, undergoes changes. The flow of charged particles that creates the signal may be temporarily choked off, only to resume later. Another idea is that the pulsar is being obscured by something drifting in front of it, a cloud of plasma or a warped disk of debris that periodically blocks our view. Whatever the cause, the effect is deeply strange. It feels less like a natural cycle and more like a deliberate act. The signal is not fading, it is gone. For those who listen, it is a period of quiet anticipation, waiting for the beacon to return. These on and off pulsars remind us that the signals we receive are not guaranteed. They are gifts of alignment and circumstance. We are only overhearing a cosmic process, and sometimes that process falls silent. It's a signal written not just as sound, but in the long, patient pauses between the broadcasts, a conversation with the universe that is punctuated by an unexplained and profound silence. Perhaps the most beautiful and subtle signal sent by pulsars is not one that can be heard, but one that can only be seen in the slow, graceful dance of their orbits. When two pulsars, or a pulsar, and another neutron star are locked in orbit around each other, they form a binary system, a pair of dead stars spiraling together through space. As they circle one another, they stir the very fabric of space-time, sending out faint ripples known as gravitational waves. These waves carry energy away from the system, causing the two stars to drift ever so slightly closer to each other with every orbit. Their dance becomes tighter, their orbital period shorter. This slow decay of their orbit is not a theory. It has been measured, and it matches the predictions of Albert Einstein's theory of general relativity with breathtaking precision. The signal is not a pulse of light or a radio wave, but the steady, inexorable shrinking of an orbit over decades of careful observation. It is a signal written in motion, a story told in the silent language of gravity. For their discovery and measurement of this effect, Russell Holtz and Joseph Taylor were awarded the Nobel Prize in Physics. They had, in effect, seen the first evidence of gravitational waves long before our modern detectors were built. They listened to the universe not with a radio dish, but by watching the slow, patient waltz of two stars in the dark. This binary system is a quiet laboratory in the sky, a place where the laws of the universe are playing out in their most elegant form. It's a reminder that some of the most profound signals are not loud or sudden, but are found in the slow, almost imperceptible changes that unfold across the long, quiet arc of cosmic time. From the steady, patient pulse of a cosmic clock, we drift now to the complete opposite, the sudden, inexplicable shouts that flare up and vanish in the blink of an eye. These are the fast radio bursts, and they are one of the greatest unsolved mysteries in modern astronomy. They are signals that do not whisper, they roar. In a few thousandths of a second, a single fast radio burst, or FRB, can release an amount of energy so vast it is difficult to comprehend. Imagine the total energy our sun produces over the course of an entire day. An FRB unleashes all of that and more in a single fleeting instant. These are not gentle flickers of light. They are cataclysmic bursts of radio waves so powerful they can be detected from galaxies billions of light years away. For a moment, they can outshine everything else in their host galaxy combined. And then they are gone. The first FRB was discovered in 2007, hidden in archival data from a telescope in Australia. It was a signal so brief, so powerful, and so strange that at first, scientists thought it might be an error, a glitch in the equipment, or even terrestrial interference from something as mundane as a microwave oven. But as more were found, all coming from the deepest reaches of space, it became clear that these were real cosmic events of a kind never seen before. What makes them so deeply mysterious is the sheer variety of their possible origins. The power they release is so immense that it rules out most ordinary stellar phenomena. These are not the flares of a normal star or the pulses of a typical pulsar. They are the product of something far more extreme. Perhaps they are the final scream of a massive star collapsing into a black hole, or the violent merger of two neutron stars, a collision that also ripples space-time with gravitational waves. Some theories even venture into more exotic territory, suggesting they could be the energetic signatures of cosmic strings, or even the technological broadcasts of a civilization far beyond our own. Each burst is a clue, a single brilliant point of light in a vast, dark map of possibilities. And with each one, we detect the mystery only deepens. The puzzle grew even more complex when astronomers discovered that some of these signals repeat. While most FRBs appear to be one-off events, a final, brilliant gasp from a dying object, a few have been observed to flash again and again from the same spot in the sky. These repeating FRBs call out from distant galaxies, sometimes in a chaotic, unpredictable pattern, and sometimes with a strange, almost periodic rhythm. One of the most famous repeaters, FRB 101.2, has been seen to burst hundreds of times. Its signals are not random. They come in clusters, active for a period of weeks, and then falling silent for months before erupting once more. It is as if something is waking up, shouting into the cosmos, and then going back to sleep. This changes everything. A repeating signal cannot be from a self-destructing event, like a stellar collapse or a merger. It must be powered by an object that can survive the blast and recharge for the next one. This has led scientists to focus on magnetars, the highly magnetic neutron stars we encountered earlier. The immense energy stored in a magnetar's magnetic field could be released in sudden violent bursts, creating the flashes we see as FRBs. A starquake on the surface of a magnetar, or a sudden reconfiguration of its magnetic field lines, could unleash the power needed. And because the magnetar itself survives, it could do so again and again. This theory is now the leading explanation, especially after a magnetar within our own Milky Way was seen to produce a burst of radio waves similar to an FRB. But even this explanation may not fit all the repeating signals. Some repeat with a strange regularity, flashing on a predictable schedule that a magnetar alone cannot easily explain. Perhaps the magnetar is orbiting another object, a star or a black hole, and its signals are only visible when it is in a certain part of its orbit. Or perhaps we are seeing something else entirely, a process we have not yet imagined. Each repeating signal is like a conversation where we can only hear one side, a series of calls from a source so far away and so powerful that it continues to defy our neatest explanations. The origin of these cosmic shouts is not the only mystery they hold. The journey of an FRB is as informative as its source. As these powerful radio waves travel across billions of light years, they pass through the vast, near-empty spaces between galaxies. This space is not truly empty. It is filled with a thin, tenuous plasma of charged particles. As the radio signal travels through this intergalactic medium, it is subtly changed. The different frequencies within the signal are slowed down by slightly different amounts, a phenomenon known as dispersion. This means that when the signal finally reaches our telescopes, the higher frequency waves arrive a fraction of a second before the lower frequency ones. By measuring this tiny time delay, astronomers can calculate how much material the signal has passed through on its journey. The greater the dispersion, the farther the signal has traveled, and the more stuff it has encountered along the way. In this sense, FRBs are not just signals, they are probes. They are cosmic messengers that carry a map of the unseen universe. They allow us to weigh the cosmos, to measure the amount of matter hidden in the vast voids between galaxies, matter that is otherwise completely invisible to us. This is the missing matter that astronomers have long been searching for, the ordinary matter that is not locked up in stars or galaxies. FRBs have found it. They have illuminated the invisible web of gas that connects the cosmic structure. It is a beautiful and quiet truth. A signal born in a cataclysmic milliseconds-long event can travel for billions of years, and in its final arrival, it brings with it a story not just of its birth, but of everything it has seen along the way. Each FRB is a pencil stroke tracing the faint, unseen architecture of the universe, revealing the hidden substance that fills the great dark oceans between the islands of light we call galaxies. From the brief, powerful shouts of fast radio bursts which tell us of violent events in the universe's adulthood, we now turn our attention to the oldest, faintest, and most profound signal of all. It is not a burst or a pulse, but a steady, silent glow that fills the entire sky, a whisper from the very dawn of time. This is the cosmic microwave background, the afterglow of the Big Bang itself. It is a signal of light released when the universe was just 3,000 years old, when the hot, dense fog of creation finally cooled enough to become transparent. This ancient light has been traveling ever since, stretched by the expansion of space into the cool, invisible microwaves we detect today. This signal is in a sense the body picture of the universe, and for the most part, it is astonishingly uniform. The temperature of this background glow is almost perfectly the same in every direction, a testament to the smoothness of the early cosmos. But almost is the key. Embedded within this uniform glow are tiny, almost imperceptible variations in temperature fluctuations that are just a few millionths of a degree warmer or cooler than the average. These faint ripples are the seeds from which all structure in the universe grew. The slightly denser, cooler spots were where gravity took hold, pulling matter together to form the first stars, galaxies, and the vast cosmic web. When we look at a map of the cosmic microwave background, we are looking at the blueprint of the cosmos. It is a signal that tells us where we came from. And for the most part, its patterns match our theories with stunning precision. But there are anomalies, strange features in this ancient light that do not quite fit quiet notes in the cosmic symphony that seem to be out of key. The most famous of these is a vast, unusually empty patch of sky known as the cold spot. It is a region of the cosmic microwave background that is significantly colder than its surroundings, and it is far larger than our standard models of cosmology would predict. This is not just a minor fluctuation. It is an enormous cold bruise on the face of the infant universe, spanning over 1 billion light-years across. Our theories tell us that the primordial fluctuations should be random, like the static on an old television screen, with no particularly large patterns. But the cold spot is not random. It is a feature, a place apart. What could have created it? One of the leading explanations is that the cold spot is the imprint of a colossal supervoid, an immense region of space between us and the ancient light that is unusually empty of galaxies. As light from the cosmic microwave background passes through such a void, it loses a tiny bit of energy, making it appear cooler to us. And indeed, astronomers have found a large, underdense region of space in the direction of the cold spot. However, this supervoid does not appear to be empty enough to explain the full extent of the coldness. The numbers don't quite add up. This has led to more exotic and speculative theories. Perhaps the cold spot is a scar from a collision, a place where our universe bumped into another bubble universe in the chaotic early moments of the multiverse. Or perhaps it is a signal of something even stranger, a texture in space-time, a remnant of a phase transition in the universe's first second. For now, no explanation is certain. The cold spot remains one of the most significant and unsettling puzzles in cosmology. It is a quiet, cold patch in the sky that whispers to us that our map of the cosmos, as beautiful and as accurate as it is, may still be missing a piece, a fundamental understanding of the universe's grandest structures. The cold spot is not the only strange feature in the universe's first light. When scientists analyzed the patterns of hot and cold spots across the entire sky, they found something else that seemed deeply improbable, a strange, unexpected alignment. The largest patterns in the cosmic microwave background, the gentle waves of temperature variation that stretch across billions of light years, are not randomly oriented as they should be. Instead, they seem to be aligned with each other, and even more strangely, aligned with the plane of our own solar system. This has been nicknamed the axis of evil, not because it is sinister, but because it is so stubbornly resistant to explanation. There is no reason why the largest structures in the entire observable universe should have any relationship to the way our little solar system happens to be oriented. It would be like discovering that all the continents on Earth are aligned with the street you live on. It feels like a coincidence, too vast to be a coincidence. Scientists have spent years trying to explain it. Perhaps it is a statistical fluke, a 1 in 1,000 chance that will disappear as we gather more data. Or perhaps it is a sign that there is something we have overlooked in our analysis, a subtle contamination from our own galaxy that is creating the illusion of a pattern. But as our instruments have become more precise, the alignment has persisted. This has led some to question our most fundamental assumptions about the universe. The cosmological principle, the idea that the universe is the same in every direction on the largest scales, is a cornerstone of modern physics. But if these alignments are real, it could suggest that the universe has a preferred direction, a large-scale structure that is not isotropic. It is a deeply unsettling thought, and one that most cosmologists are reluctant to embrace without more evidence. For now, the axis of evil remains a quiet statistical anomaly, a signal hidden in the noise that hints at a cosmic order we do not understand, a connection between the largest scales of creation and our own small place within it that simply should not be there. The cosmic microwave background sends us signals not just in its temperature, but in its light's orientation. This is known as polarization. Just as sunglasses can filter light waves that oscillate in a certain direction, the ancient light from the Big Bang is polarized, carrying a faint but measurable pattern. This polarization is a signal that tells us about the last moments before the universe became transparent. There are two types of polarization patterns that astronomers search for in this ancient light: E modes and B modes. E modes are gentle radial patterns created by the movement of matter in the early universe, and they have been detected with high precision. They are another beautiful confirmation of our standard cosmological model. But the true prize is the search for B modes, which are fainter swirling patterns. Primordial B modes are believed to be the unique signature of gravitational waves, ripples in space-time itself, that were generated during the explosive period of cosmic inflation in the universe's first fraction of a second. Detecting these primordial gravitational waves would be like hearing the echo of the Big Bang itself. It would be the smoking gun for inflation, confirming that the universe underwent this period of incredible superluminal expansion at its birth. The signal would be unimaginably faint, a tiny swirling pattern hidden in the faint glow of the cosmos. Several times, research teams have announced the potential detection of these B modes, only to discover later that the signal was contaminated by the dust within our own Milky Way, which also produces polarized light. The search continues, With ever more sensitive telescopes placed in the driest, coldest parts of the world or launched into space, scientists are listening for this faint, swirling signal. It is one of the most ambitious quests in modern science. The detection of primordial B modes would open a window onto the physics of the universe at energies far beyond anything we can create on Earth. It would be a signal not of a star or a galaxy, but of the birth of space-time itself, a quiet, ancient twist in the light that tells us the story of how everything began. From the ancient frozen light of the cosmic microwave background, a signal that tells us of the universe's birth, we drift now to a sound that was predicted a century ago, but heard for the first time only recently. This is not a signal of light or radio, but of gravity itself. It is a murmur in the very fabric of reality, a ripple in space-time. These are gravitational waves, and learning to hear them has opened a new silent window onto the cosmos. For 100 years, they were only a beautiful prediction in Albert Einstein's theory of general relativity. He imagined that massive accelerating objects like two black holes spiraling into each other would not just move through space, but would shake it, sending out waves of gravitational energy that travel at the speed of light. These waves would stretch and squeeze space-time itself, but the effect would be so astonishingly small that Einstein himself doubted we would ever be able to detect it. By the time a wave from a distant cosmic collision reached Earth, it would distort a detector several miles long by less than the width of a single proton. And yet, in 2015, we heard it. Two incredible instruments, part of the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected the first signal. It was a sound that lasted for less than a second, a faint rising chirp that swept up in frequency before abruptly stopping. That tiny fleeting sound was the echo of one of the most violent events in the universe. The collision of two black holes, each about 30 times the mass of the Sun, in a galaxy over 1 billion light-years away. In the final moments of their cosmic dance, they were circling each other hundreds of times per second, moving at nearly the speed of light. And then they merged, creating a single larger black hole and converting the mass of 3 entire suns into pure gravitational energy in a fraction of a second. That burst of energy was for a moment more powerful than all the light from all the stars in the observable universe combined. But it was a silent power, a storm not of light, but of space-time. The signal, when translated into sound, is a simple, beautiful chirp. But in that sound, we can hear the story of a cosmic catastrophe that unfolded 1 billion years ago. We can hear the masses of the black holes, the speed of their spiral, and the final quiet ring of the new black hole as it settled into stillness. It was the first time humanity had ever heard the universe sing in the language of gravity. Since that first detection, the symphony has grown. Gravitational wave observatories have heard the signals of dozens more black hole mergers, but they have also detected something else. Something that creates not only a ripple in space-time, but also a brilliant flash of light. In 2017, for the first time, we heard the signal of 2 neutron stars colliding. Neutron stars are the ultra-dense remnants of dead stars, and their merger is an event of unimaginable violence. The gravitational wave signal was longer than that of a black hole merger, a rising chirp that lasted for nearly a minute. But what made this event so revolutionary was that just 7 seconds after the gravitational wave signal ended, telescopes around the world saw a burst of gamma rays from the same patch of sky. For the first time, we had both seen and heard the same cosmic event. An astronomer's dream come true. In the days and weeks that followed, telescopes watched as a new light appeared in the sky, a kilonova, the glowing radioactive aftermath of the collision. By studying the light from this kilonova, scientists were able to see the chemical fingerprints of heavy elements like gold, platinum, and uranium being forged in the explosion. For a long time, we had wondered where the heaviest elements in the universe came from. Normal stars can't make them. Supernovae can't make enough of them. The collision of these two neutron stars provided the answer. That single, beautiful event, heard as a gravitational chirp and seen as a fading glow, created thousands of Earth masses of gold and other precious metals, scattering them into space. It is a profound and humbling thought. Every piece of gold on Earth, every ring, every coin, was likely born in the cataclysmic collision of two dead stars, a process we have now heard with our own ears from a galaxy 130 million light-years away. The signal was a whisper, but it told us the origin story of the universe's most precious treasures, forged in a fire that was both silent and blindingly bright. The individual chirps of black holes and neutron stars are the loud notes in the cosmic symphony. But some scientists are listening for something much quieter, something that is always there. This is the gravitational wave background, a constant, gentle hum of space-time, ripples coming from all directions at once. This background hum is thought to be the combined murmur of countless cosmic events too small or too distant to be detected individually, but which together create a faint stochastic noise. Imagine being on a still lake at night. You can hear the loud splash of a large fish jumping, but beneath that, there is the constant soft lapping of 1,000 tiny ripples against the shore. The gravitational wave background is like that lapping sound. It could be the blended chorus of millions of merging binary systems throughout the universe. Or it could have a more ancient origin, a faint echo of the chaotic inflationary period in the universe's first second. Detecting this background signal is incredibly challenging. It is far fainter than the signals from individual mergers. But scientists are searching for it using arrays of pulsars. By monitoring the incredibly precise timing of millisecond pulsars scattered across our galaxy, they hope to detect the subtle correlated stretching and squeezing of space-time as this background hum passes through. A successful detection would give us a new map of the universe, one written not in light, but in the constant gentle tremor of reality itself. It would be like finally hearing the ambient sound of the cosmos, the quiet, ever-present music that has been playing unheard since the dawn of time. While LIGO and other Earth-based observatories have opened the era of gravitational wave astronomy, they are deaf to some of the universe's most profound sounds. They can only hear the high-frequency chirps of small, fast-merging objects. They cannot hear the slow, deep bass notes of the cosmos, the signals from supermassive black holes. These giants, millions or billions of times the mass of our sun, lie at the heart of nearly every galaxy. And sometimes they merge too. When two galaxies collide, their central black holes will slowly spiral towards each other over millions of years, locked in a slow, majestic dance. In their final years, They will be emitting powerful low-frequency gravitational waves, signals that have a wavelength of light years. To hear these signals, we need a detector the size of a solar system, and that is exactly what scientists are building. The Laser Interferometer Space Antenna, or LISA, will be a constellation of 3 spacecraft flying in a triangular formation, millions of miles apart. They will be connected by laser beams, forming a giant gravitational wave detector in space. LISA will be able to hear the slow, deep mergers of supermassive black holes anywhere in the universe. It will hear the sound of small stars and black holes being swallowed by these giants. It will even be able to detect the faint primordial hum from the Big Bang with a clarity that Earth-based detectors can only dream of. The mission is still years away, but it promises to revolutionize our understanding of the cosmos. It will allow us to listen to the growth of galaxies, to map the dark side of the universe, and to hear the story of how the giants at the heart of galaxies came to be. It will be a new sense for humanity, a way to hear the silent, slow, and powerful music that has been shaping the universe since its very beginning. From the gentle space-time warping hum of gravitational waves, we return now to signals of a different kind of power. A power born not from mass alone, but from a force that can twist, snap, and erupt with an energy that almost defies belief. We drift into the realm of the magnetic monsters of the cosmos, the magnetars. A magnetar is a type of neutron star, the collapsed core of a giant star. But it is a neutron star with a difference. It possesses a magnetic field of truly unimaginable strength. A typical refrigerator magnet has a field of about 50 Gauss. The Earth's magnetic field, which guides our compasses, is about half a Gauss. A magnetar's magnetic field can be 1,000 trillion Gauss. That is 1 billion times stronger than the most powerful magnet ever created on Earth. It is a force so strong it would warp the atoms in your body from 1,000 miles away. A force so intense that it makes the very vacuum of space around it behave in strange ways. These magnetic fields are not stable. They are twisted and stressed, and sometimes they snap. When this happens, a starquake ripples across the surface of the neutron star, and an immense burst of energy is released. These are magnetar flares, and they are some of the most powerful explosions in the universe. In a fraction of a second, a magnetar can release more energy than our sun will produce in 100,000 years. We detect these events as intense bursts of gamma rays and X-rays. On December 27, 2004, such a flare from a magnetar halfway across the galaxy struck the Earth. It was so powerful that it partially ionized our upper atmosphere, disrupting radio communications. The signal came from an object just 12 miles wide, 20,000 light years away, and for a moment it was brighter in our sky than anything outside the solar system. These flares are a signal of the incredible energy that can be stored in a magnetic field. They are a reminder that some of the most powerful objects in the universe are not the largest, but the most compact and the most intensely magnetized. The discovery that some fast radio bursts repeat led scientists to suspect a connection to magnetars. A repeating signal needs a source that can survive its own eruption, and a magnetar fits the description perfectly. Its immense magnetic reservoir could power multiple bursts over time. For years, this was the leading theory, but the proof was missing. The FRBs were all coming from distant galaxies, too far away to see the source clearly. Then, in April of 2020, it happened. A magnetar within our own Milky Way, about 30,000 light-years away, let out a burst of radio waves. It was less powerful than the FRBs from other galaxies, but it had all the same characteristics. It was a brief, brilliant flash of radio energy. For the first time, we had seen an FRB from our own cosmic backyard, and we knew exactly what had created it. It was the smoking gun, the confirmation that magnetars can and do produce these mysterious cosmic shouts. It doesn't mean that all FRBs come from magnetars. The single cataclysmic bursts may still be from other events like merging neutron stars, but it solved a major piece of the puzzle. The signal was a bridge connecting two of the most fascinating mysteries in modern astronomy. It showed us that the same magnetic monsters that produce gamma-ray flares can also shout in the language of radio. It was a moment of beautiful clarity when two separate streams of cosmic signals were found to flow from the same incredible magnetic source. The immense energy of a magnetar flare is born from a tremor on its surface, a starquake. The crust of a neutron star is the strongest material known in the universe, a crystalline lattice of atomic nuclei. But even this material can be stressed to its breaking point by the shifting, twisting magnetic field beneath it. When the crust finally cracks, seismic waves ripple across the star, and a burst of energy is released. But these are not the only sounds a magnetar makes. In the aftermath of a giant flare, astronomers have detected something else, a fainter pulsing signal that rings like a bell. These are the quasi-periodic oscillations, or QPOs. They are thought to be the sound of the star itself vibrating, ringing from the force of the starquake. The frequencies of these oscillations are a direct signal from the star's interior, a form of stellar seismology that allows us to probe the exotic physics of matter at densities we can never replicate on Earth. By studying the tone of these vibrations, we can learn about the composition of the star's crust, the nature of the superfluid in its core, and the way its magnetic field is anchored. It is as if the starquake strikes the magnetar like a hammer, and by listening to the fading ring, we can understand what it is made of. It is one of the most delicate and informative signals we can receive from these cosmic monsters. It is the sound of a star 12 miles wide and 1,000 trillion times more magnetic than our world, quietly trembling in the aftermath of its own unimaginable fury. The power of a magnetar is so extreme that it can even affect the vacuum of space itself. According to quantum electrodynamics, the vacuum is not truly empty. It is a seething foam of virtual particles that pop into and out of existence in fleeting instants. In the presence of an incredibly strong magnetic field like that of a magnetar, this vacuum can be changed. It can become birefringent, meaning it can split a beam of light into two different polarizations. This effect was predicted decades ago, but was thought to be impossible to observe. However, in 2016, astronomers studying the light from a magnetar found the first evidence that it might be happening. The light passing through the star's intense magnetosphere showed signs of this strange polarization splitting. It was a signal, not from the star itself, but from the empty space around it. It is a profound and deeply strange discovery. It means that a magnetar's magnetic field is so strong that it can alter the fundamental properties of reality in its vicinity. It is a force of nature that can literally twist the void. When we receive the light from a magnetar, we are not just seeing a star. We are seeing a region of space where the laws of physics are being bent into new and unfamiliar shapes. The signal is a quiet testament to the fact that even nothing can be changed by the presence of one of these incredible magnetic beasts. From the violent magnetic heart of dead stars, we journey now even farther across billions of light years and billions of years in time to listen to the signals from the universe's brilliant youth. These are the quasars, the brightest and most distant objects we can see, and their light is a message from an era when the cosmos was young, chaotic, and filled with a fire that has long since faded. A quasar is not a star. It is the intensely luminous heart of a young galaxy, powered by a supermassive black hole feeding on a furious diet of gas dust and stars. As matter swirls into the black hole, it forms a vast hot disk called an accretion disk. Friction and gravity heat this disk to millions of degrees, causing it to blaze with a light that can outshine 1 trillion stars. For a time, the center of the galaxy glows with a brilliance that can be seen across the entire observable universe. Because their light has taken so long to reach us, the quasars we see today are windows into the distant past. We see them as they were 10, 12, even 13 billion years ago. They are beacons of deep time signals that tell us the story of how the first galaxies grew, how the first supermassive black holes formed, and how the universe emerged from its dark ages. Their light is a kind of fossil, a perfectly preserved echo of a younger, more turbulent cosmos. When we study the spectrum of a quasar's light, we can see the chemical fingerprints of the gas clouds it has passed through on its long journey, allowing us to map the invisible structure of the universe in its infancy. Each quasar is a lighthouse shining from the far shore of cosmic history, illuminating the dark, empty spaces that lie between then and now. The light from a quasar is not a steady, constant glow. It flickers, it brightens, and dims, sometimes over the course of years, and sometimes in just a matter of hours. This variability is a signal from the very heart of the engine powering the quasar. The flickering is thought to be caused by instabilities in the accretion disk, the swirling vortex of matter that feeds the black hole. Flares, hotspots, and turbulent eddies in the disk can cause sudden changes in its brightness. By studying the timing and pattern of this flickering, astronomers can learn about the processes happening just outside the black hole's event horizon, a region we can never see directly. The speed of the flickering gives us a clue about the size of the accretion disk itself. If a quasar's light changes over the course of a day, it means the light-emitting region cannot be much larger than a light day across. This helped confirm that the engines of quasars must be incredibly compact, consistent with the supermassive black hole model. The light from a quasar is a chaotic, shimmering signal, a story of violence and fury told in a language of flickering light. It is the sound of a monster feeding the roar of a cosmic engine running at full throttle. And by listening to the rhythm of its chaotic pulse, we can begin to understand the physics of the most extreme environments in the universe, the fiery boundary between ordinary matter and the endless silence of a black hole. For a long time, quasars were always found at the heart of massive, bright galaxies. It was a neat picture, A giant galaxy provides the fuel to power the giant black hole at its center. But as our telescopes have peered deeper into the cosmos, we have found something strange: quasars that appear to be alone. These are lonely quasars, brilliant beacons of light that seem to have no host galaxy around them at all. What could this mean? Has the host galaxy been stripped away in a collision with another galaxy, leaving the black hole to wander alone through intergalactic space? Or are these quasars living in galaxies that are made almost entirely of dark matter, with very few stars, making them nearly invisible to our telescopes? Another possibility is that the light from the quasar itself is so overwhelmingly bright that it simply drowns out the faint light of the stars in its host galaxy, making it impossible for us to see. The James Webb Space Telescope is now helping to solve this mystery. With its incredible sensitivity, it can peer into the faint halos around these quasars, searching for the ghostly light of their hidden homes. Whatever the answer, these lonely quasars are a signal that our understanding of the relationship between black holes and galaxies may not be complete. They are a reminder that the universe is filled with exceptions, with strange and beautiful outliers that defy our tidy models and force us to imagine new possibilities. Sometimes, the universe plays tricks with light, and the signal from a single quasar can reach us in multiple beautiful forms. This is the phenomenon of gravitational lensing, which we have touched on before. If a massive galaxy or cluster of galaxies lies directly between us and a distant quasar, its immense gravity can bend and warp the space-time around it, acting like a giant cosmic lens. This lens can distort the light of the quasar, smearing it into arcs or creating multiple images of the same object. One of the most famous examples is the Einstein cross, a stunning configuration where the light from a single, distant quasar is split into 4 separate images, arranged in a cross-like pattern around the core of a foreground galaxy. We are seeing 4 signals, but they all come from one source. What makes this even more fascinating is that the light from each of these images travels a slightly different path through the warped space-time of the lensing galaxy. This means the light from one image can arrive at Earth months or even years before the light from another. If the quasar flickers in brightness, we will see that flicker in one image first, and then later, we will see the same flicker in the other images, like a series of cosmic echoes. This time, delay allows astronomers to measure the expansion rate of the universe, the Hubble constant, with a new and independent method. By measuring the delay and the geometry of the lens, they can calculate the absolute distances involved. The Einstein cross is more than just a beautiful illusion. It is a signal that has been split and reassembled by gravity, a cosmic gift that allows us to see the same moment in history multiple times, and in doing so, to measure the very fabric of the cosmos. From the ancient brilliant light of quasars, we now turn our attention to signals that are almost the opposite. They are not light, they have almost no mass, and they pass through nearly everything as if it were not there. These are the neutrinos, the ghost particles of the cosmos. Trillions of them are streaming through your body every second, and you will never feel a single one. They are born in the hearts of stars, in violent supernovae, and in the chaotic engines of distant galaxies. And they travel across the universe almost completely unimpeded, carrying messages from places we can never see with light. For a long time, the only neutrinos we could detect were were the low-energy ones from our own sun. But in 2013, the IceCube Neutrino Observatory, a giant detector buried a mile deep in the Antarctic ice, detected the first high-energy neutrinos from beyond our solar system. These were particles with energies 1,000,000 times greater than solar neutrinos, and they were a signal that something incredibly violent was happening somewhere in the deep cosmos. But where were they coming from? Neutrinos travel in a perfectly straight line, unbent by magnetic fields, so they should point directly back to their source. But for years, their origins remained a mystery. Then, in 2017, a breakthrough. IceCube detected a single, very high-energy neutrino. An alert was sent out to telescopes around the world, and they all pointed in the direction the neutrino had come from. And there, they found it, a blazar, a type of galaxy with a supermassive black hole at its center that is firing a jet of particles directly at us. The blazar was in the middle of a powerful flare, and for the first time, we had matched a ghost particle to its fiery home. It was a landmark moment in astronomy. It confirmed that blazars are cosmic particle accelerators capable of flinging neutrinos across billions of light years. These high-energy neutrinos are a new kind of signal, a new way to see the universe. They are messengers from the most extreme environments, places so dense and chaotic that light cannot escape. But the neutrinos, with their ghostly ability to pass through anything, can. They bring us stories from the hearts of cosmic engines, whispers from a world that would otherwise be completely invisible. The neutrinos we have detected come in 3 flavors, and they have the strange quantum ability to change from one flavor to another as they travel. But some theories predict the existence of a 4th type, a sterile neutrino. This hypothetical particle would be even more ghostly than the others. It would not interact through any of the fundamental forces of nature except gravity. It would be, for all intents and purposes, a piece of the universe that is completely invisible to us, detectable only through its subtle gravitational influence. The existence of sterile neutrinos could solve several deep mysteries in physics. It could help explain the origin of neutrino mass, and it could even be a candidate for dark matter, the mysterious unseen substance that makes up most of the matter in the universe. Scientists are searching for the signal of sterile neutrinos in a variety of ways. They look for tiny anomalies in nuclear decay experiments, and they search for subtle gaps in the spectrum of neutrinos coming from nuclear reactors. The search is incredibly difficult, like trying to find a ghost in a storm of other ghosts. So far, the evidence is tantalizing, but inconclusive. Some experiments have hinted at the existence of sterile neutrinos, while others have found nothing. The signal, if it exists, is at the very edge of our ability to detect. But if it is found, it would be a revolution. It would mean that there is a whole new type of matter in the universe, a particle that is part of a hidden sterile sector of reality that barely interacts with our own. It would be a signal that the universe is even stranger and more populated with unseen things than we ever imagined. While neutrinos are ghostly, they are not the only high-energy particles that rain down on Earth from space. These are the cosmic rays, mostly protons and atomic nuclei, that have been accelerated to near the speed of light by violent cosmic events. For decades, we have been detecting these particles, but their origins have often been a mystery. Then, in 1991, the Fly's Eye experiment in Utah detected something that seemed impossible. It was a single subatomic particle, likely a proton, that was traveling at 99.9 0.51% the speed of light. It was moving so fast that if it were in a race with a beam of light, it would have lost by less than the width of an atom over the course of a year. It struck the Earth's atmosphere with the kinetic energy of a baseball, traveling at 60 miles per hour. A single invisible particle carrying the energy of a macroscopic object. It was nicknamed the "Oh my God" particle for the reaction of the scientists who discovered it. The mystery of this particle is its energy. There is no known object in our galaxy that is powerful enough to accelerate a particle to such an incredible speed. Whatever created it had to be one of the most energetic phenomena in the universe, like the jets of a giant radio galaxy or a gamma-ray burst. And it had to be relatively close by, cosmically speaking, because a particle with this much energy should lose it quickly by interacting with the faint microwave background that fills all of space. Since that first detection, a few dozen more of these ultra-high-energy cosmic rays have been seen, but their origins are still debated. They seem to come from random directions in the sky with no clear source. They are a signal of a cosmic accelerator somewhere out there that is more powerful than anything we can imagine. They are the fastest, most energetic messengers we have ever received, and they bring with them a profound and unanswered question. What in the universe has this much power? While the high-energy neutrinos and cosmic rays from deep space are rare and exotic signals, there is another stream of particles that is constant, gentle, and ever-present. These are the neutrinos from our own sun. The nuclear fusion reactions that power the sun's core produce an unimaginable number of them. Every second, more than 100 trillion solar neutrinos pass through your body. They stream out of the sun's heart, pass through its dense layers, through the vacuum of space, through the entire Earth, and through you without ever stopping or interacting. For a long time, this presented a puzzle. Our theories of the sun predicted a certain number of neutrinos, but our experiments on Earth were only detecting about a third of that number. This was the solar neutrino problem, and it was a deep crisis in physics. Did we not understand the sun, or did we not understand neutrinos? The answer, it turned out, was the latter. We discovered that neutrinos can change their flavor as they travel. The sun was producing the predicted number of neutrinos, but by the time they reached Earth, 2/3 of them had changed into flavors our detectors couldn't see. The solution to this puzzle was a triumph of physics, and it proved that neutrinos have mass, a discovery that has profound implications for our understanding of the universe. The solar neutrino stream is a constant silent signal from the heart of our own star. It is a message that took decades to decipher, but it taught us something fundamental about the nature of matter and the strange quantum world of these beautiful, ghostly particles. From the fleeting, ghostly particles that pass through us without a trace, we turn our attention to the great silent presences of the cosmos, the unseen substances that shape the universe on its grandest scales. We cannot see them, we cannot touch them, but we can detect their signals, written in the motion of stars and the bending of light. These are the mysteries of dark matter and dark energy. One of the most beautiful and compelling signals of dark matter's existence comes from gravitational lensing. As we have seen, the gravity of a massive object can bend the path of light that passes by it. When we look at a distant cluster of galaxies, the combined gravity of all the stars, gas, and dark matter in that cluster acts as a giant lens. It magnifies and distorts the light from the galaxies that lie behind it, smearing their images into strange, beautiful arcs and rings of light. By measuring the exact shape and distortion of these lensed images, astronomers can calculate how much mass must be in the cluster to create such a powerful lens. And time again, the answer is far more than we can see. The amount of mass required to produce the observed lensing is 5 to 10 times greater than the mass of all the visible stars and gas combined. The rest is dark matter. Gravitational lensing gives us a way to see the invisible. It allows us to map the distribution of dark matter in galaxy clusters and throughout the cosmic web. These maps show us that dark matter forms a vast unseen scaffold upon which the visible structures of the universe are built. The signal is not a sound or a particle, but a silent distortion in the light from the most distant galaxies. It is a message from the unseen, a beautiful warped echo that tells us that most of the universe is hidden from our eyes, its presence revealed only by the gentle, patient way it bends the light that travels through it. The first signal that something was deeply wrong with our understanding of the universe came not from distant galaxy clusters, but from our own cosmic neighbors. In the 1970s, astronomer Vera Rubin was studying the rotation of spiral galaxies. She expected to find that the stars in the outer parts of the galaxies would be moving more slowly than the stars in the inner parts, just as the outer planets in our solar system move more slowly than the inner planets. This is simple Newtonian gravity. The farther you are from the central mass, the weaker its pull, and the slower you orbit. But that is not what she found. In galaxy after galaxy, she discovered that the stars in the outer regions were moving just as fast as the stars near the center. They were rotating far too quickly. By all rights, these stars should have been flung off into intergalactic space, like children flying off a merry-go-round that is spinning too fast. The visible matter in the galaxies, the stars and gas we could see, did not provide enough gravity to hold them in their orbits. The conclusion was inescapable. There had to be a huge amount of unseen matter in these galaxies, a vast invisible halo of mass that extended far beyond the visible disk of stars. This was the first strong evidence for dark matter. The signal was the unexpectedly fast rotation of the stars. It was a signal written in the quiet, steady motion of a billion suns, and it told us that the galaxies we see are just the bright, visible tips of much larger, darker, and more mysterious structures. It was a revolution that began with a simple, careful measurement of speed, a discovery that revealed that 90% of the universe's matter was missing. For decades, we have searched for the particles that make up this dark matter, and for just as long, we have come up empty. But what if dark matter isn't a new particle at all? Some theories propose that it could be made of primordial black holes that were not formed from the collapse of stars, but were created in the hot, dense chaos of the universe's first second. These black holes could be of any size from the mass of an asteroid to thousands of times the mass of our sun. If they exist, they would be incredibly difficult to detect. They would be dark, compact, and scattered throughout the universe, but they would still have gravity. They could act as the unseen mass that holds galaxies together, and they might send their own subtle signals. If a primordial black hole passes between us and a distant star, it could act as a tiny gravitational lens, a microlens causing the star to briefly brighten. Searches for these micro-lensing events have been conducted, but they have not found enough to account for all the dark matter. Another signal could come from the very end of their lives. According to Stephen Hawking, black holes are not completely black. They slowly evaporate over immense timescales by emitting Hawking radiation. A small asteroid mass black hole created in the Big Bang might be reaching the end of its life right now, vanishing in a final weak flash of gamma rays. Telescopes have searched for these faint dying gasps, but so far, none have been found. The theory remains beautiful, speculative, and unproven. A universe where the unseen matter is made of the silent ancient ghosts of the Big Bang itself. While dark matter holds the universe together with its gravity, there is another, even more mysterious substance that is doing the exact opposite. It is pushing the universe apart. This is dark energy. The signal of its existence came in the late 1990s when two teams of astronomers were studying distant supernovae to measure how the expansion of the universe was slowing down. They were using a special type of supernova, a type Ia, as a standard candle. These explosions always have the same intrinsic brightness, so by measuring how faint they appear, we can calculate how far away they are. When they looked at the most distant supernovae, they found something that no one expected. The supernovae were fainter than they should have been. They were farther away than our models predicted. The only way to explain this was if the expansion of the universe was not slowing down, but speeding up. It was a discovery that turned cosmology on its head and won the Nobel Prize. There is some unknown energy inherent in the fabric of space-time itself, a kind of cosmic anti-gravity that is causing galaxies to fly away from each other at an ever-increasing rate. We call it dark energy, but this is just a name for our ignorance. We have no idea what it is. It makes up nearly 70% of the energy density of the universe. Yet its nature is a complete mystery. The signal of dark energy is the subtle, unexpected faintness of the most distant dying stars. It is a message that tells us the ultimate fate of the universe may not be a fiery collapse, but a cold, lonely expansion that will eventually pull every galaxy out of our sight, leaving our own Milky Way as a solitary island in an endless, empty void. From the invisible forces that shape our universe's destiny, we drift now to the visible patterns. They create the grand architecture of the cosmos, written in the distribution of light across billions of years. When we map the universe on its largest scales, we find that galaxies are not scattered randomly like dust. They are arranged in a magnificent, intricate structure known as the cosmic web. This web is made of vast, thread-like filaments of galaxies stretching for hundreds of millions of light years, connecting dense clusters of galaxies at their intersections. And between these filaments lie immense dark and astonishingly empty regions known as cosmic voids. These filaments and voids are the largest structures in the universe. They are the signal of gravity's patient work, over 13 billion years, amplifying the tiny random fluctuations from the Big Bang into a structure of breathtaking complexity and beauty. The cosmic web is the skeleton of the universe, and the galaxies are the faint lights that trace its form. When we look at a map of the cosmic web, we are seeing the outcome of the cosmic battle between the pull of dark matter, which draws matter together into filaments, and the push of dark energy, which expands the voids and drives everything apart. The signal of this structure is not a single message, but the pattern itself. It is the quiet statistical truth that emerges when you plot the position of a million galaxies. It is a reminder that everything is connected, that our own Milky Way is not an isolated island, but a small part of a vast, interconnected continent of light drifting in an ocean of darkness. In recent years, as our radio telescopes have surveyed the sky with greater sensitivity, they have begun to find structures that do not fit neatly into our picture of the cosmic web. These are the odd radio circles, or ORCs. They are enormous, faint rings of radio emission, some of them a million light years across, that seem to have no obvious galaxy or cluster at their center. They are ghostly circles hanging in intergalactic space with no clear explanation for what created them. Are they the remnants of a gigantic shock wave from some explosive event in a distant galaxy? An event so powerful that its spherical shell of debris has expanded to incredible size. Perhaps they are the result of the outflow from a supermassive black hole, or the aftermath of the merger of two black holes. Or could they be something more exotic, like the throat of a wormhole seen face on? At present, we simply don't know. The signals are faint, and only a handful have been discovered so far. They are a new cosmic mystery, a signal that there are processes happening in the vast empty spaces between galaxies that we are only just beginning to see. They are like smoke rings in the dark, their form hinting at a powerful event that is long over, leaving behind only a silent, expanding ghost of a circle in the radio sky. The cosmic web is not just made of galaxies, it is also illuminated by them. The gas that fills the vast filaments of the web is mostly dark and invisible. But when it is illuminated by the intense light of a quasar or a star-forming galaxy, it can glow with a faint fluorescent light. In recent years, astronomers have been able to directly image this faint glow, revealing the cosmic filaments for the first time. They have seen vast, shimmering threads of hydrogen gas stretching for millions of light years, connecting distant galaxies. It is like seeing a spider's web for the first time by the way it catches the morning dew. These images are a stunning confirmation of our cosmological models. They show us that the invisible skeleton of the universe is real. The signal is the faint, almost imperceptible light from the most diffuse matter in the cosmos, a glow that is 1,000,000 times fainter than the darkest night sky on Earth. Detecting it requires hours of exposure with the most powerful telescopes in the world. But it is there, a quiet, beautiful signal that reveals the hidden rivers of gas that flow between galaxies, the channels that feed their growth, and trace the grand underlying structure of all that is. In stark contrast to the glowing filaments, there are the cosmic voids. The largest of these is the Bootes void, sometimes called the Great Nothing. It is a colossal, almost spherical region of space, nearly 330 million light-years in diameter, that is astonishingly empty. If our Milky Way were at the center of the Bootes void, we would not have known that other galaxies existed until the 1960s. The nearest one would be millions of light-years away. While our models of the universe predict the existence of voids, the Bootes void is larger than most would expect. It is a signal of emptiness on a scale that is difficult to wrap our minds around. It is a place where the expansion of the universe has won its battle with gravity so completely that it has swept the region almost clean of matter. To look in the direction of the Bootes void is to look at a great dark ocean of nothing. It is a quiet, humbling reminder of the scale of the cosmos. It tells us that the universe is not only defined by the things it contains, but also by the vast, silent absences in between. It is a signal that even nothing can be a structure, a feature as grand and as informative as the brightest cluster of galaxies. From the grand, continent-sized structures of the cosmos, we return now to the individual points of light that compose them, the stars. They seem from our great distance to be steady, eternal flames. But when we look closely, we find that many of them are sending their own strange and enigmatic signals, not in radio or gravity, but in the subtle, rhythmic, and sometimes chaotic flickering of their own light. There are entire classes of stars known as variable stars. Stars whose brightness changes over time. Some, like the Cepheid variables, pulsate with a rhythm so regular and predictable that they can be used as standard candles to measure the distances to other galaxies. Their light breathes in and out, swelling and shrinking over the course of days or weeks, and the period of their pulse is directly related to their true brightness. They are the lighthouses of the cosmic ocean, their steady rhythmic signal, allowing us to map the shores of galaxies millions of light years away. But other variable stars are not so regular. Their light flickers and flares with a chaotic, unpredictable rhythm. Some are young stars, still settling down their light, obscured by swirling disks of gas and dust. Others are old, dying stars, sputtering and coughing as they enter their final stages. Each one is a signal, a story of a star's life told in a language of changing light. By listening to the quiet, subtle rhythm of their flicker, we can learn about their age, their size, and the processes happening deep within their fiery hearts. Among the billions of stars in our galaxy, a few stand out as deeply, profoundly strange. One of the most mysterious is Przybylski's star. It is a star whose light sends a signal that should be impossible. When astronomers study the light from a star, they can see the chemical fingerprints of the elements it contains. Most stars are made primarily of hydrogen and helium, with trace amounts of heavier elements like carbon, oxygen, and iron. But Przybylski's star is different. Its spectrum is a chemical chaos. It has very little iron, but it is incredibly rich in bizarre heavy elements like strontium, cesium, and even radioactive elements like promethium and einsteinium elements that should not exist in a star because they decay so quickly. It is as if the star has dredged up the strangest, most exotic materials from the periodic table and displayed them in its atmosphere. No one knows how to explain it. Is the star a magnetic anomaly, somehow trapping and concentrating these heavy elements on its surface? Is it the remnant of a strange type of supernova we have never seen before? Or has it been polluted by a nearby explosion or a collision with an exotic object? Some have even speculated quite wildly that it could be a sign of alien technology, a star being used as a cosmic waste dump for nuclear materials. For now, the star remains a complete enigma. Its light is a signal of a chemical composition that defies our understanding of how stars work. A quiet, shining question mark in the southern sky. While some stars send strange signals in their light, others send a signal in their sudden, inexplicable absence. We often think of the death of a massive star as a supernova, a brilliant explosion that can briefly outshine its entire galaxy. But what if a star could die without a sound, without a flash of light? This is the idea of a failed supernova. In this scenario, a very massive star reaches the end of its life, and its core collapses under its own gravity. But instead of triggering a massive explosion that blows the outer layers of the star into space, the collapse is so complete and so rapid that the core collapses directly into a black hole, and the outer layers of the star simply fall into it and disappear. There is no brilliant flash, no expanding cloud of debris. The star simply vanishes from sight. Have we ever seen this happen? Possibly. There have been a few cases where astronomers have been observing a massive star, only to look back a few years later and find that it is gone. There is no supernova remnant, no sign of an explosion. The star has simply blinked out of existence. It is a difficult observation to confirm. The star could have just dimmed dramatically or been obscured by dust. But the possibility is tantalizing. It is the quietest, most subtle signal of a star's death. Not a roar of light and fire, but a silent, final closing of a door, as a giant of the cosmos falls into itself and is seen no more. In the ancient, densely packed star clusters that orbit our galaxy, there are stars that seem to be in the wrong place at the wrong time. These are the globular clusters, spherical collections of hundreds of thousands of stars, all born at the same time, more than 10 billion years ago. All the stars in a globular cluster should be old red and faint. But when we look at them, we find a scattering of stars that are bright blue and appear to be young. These are the blue stragglers. They are a signal that something has disrupted the normal quiet aging process of these ancient stellar cities. How can a star in a 10 billion year old cluster look like it is only a few 100 million years old? The leading theory is that they are the result of stellar mergers or collisions in the crowded heart of a globular cluster. Two old faint stars can sometimes collide and merge, or a binary star system can slowly spiral together. The result is a single, more massive star with a new reservoir of hydrogen fuel in its core. This new star begins to burn hot and bright, appearing blue and young, a straggler in the race of stellar evolution. Blue stragglers are a signal of the hidden dynamic life of star clusters. They are a reminder that even in the oldest, quietest corners of the galaxy, things are not always as they seem, and that even old stars can sometimes find a way to be born again. As our journey through the cosmic signals brings us closer to home, we find that our own Milky Way galaxy is filled with as many mysteries as the most distant quasars. We are living inside a vast, spinning city of stars, and from our quiet neighborhood in one of its spiral arms, we can hear the strange whispers and see the ghostly structures of our galactic home. At the very heart of our galaxy, 26,000 light-years away, in the direction of Sagittarius, lies a supermassive black hole named Sagittarius A. It is 4 million times the mass of our Sun, a silent gravitational anchor around which our entire galaxy revolves. We cannot see the black hole itself, but we can see the signals from the chaotic environment around it. We see stars whipping around it at incredible speeds, their orbits a testament to its immense gravity. And we hear a signal in the radio. Sagittarius A is a powerful compact source of radio waves. This radio emission is not steady. It flickers and flares, sometimes brightening by a factor of 100 in just a matter of hours. This flickering is a signal from the matter that is being heated as it spirals into the black hole. It is the sound of the monster feeding. By studying these radio flares, we are listening to the final moments of gas and dust before they cross the event horizon and are lost forever. It is a chaotic, turbulent signal from the very heart of our galaxy, a whisper from the edge of an abyss, telling us that even the silent center of our home is a place of incredible violence and power. When we look toward the galactic center, not in radio waves, but in high-energy gamma rays, we see something even stranger, a structure so vast and so unexpected that it was only discovered in the last decade. These are the Fermi bubbles. They are two colossal hourglass-shaped lobes of hot gas and high-energy particles extending for 25,000 light-years above and below the plane of our galaxy. They are ghostly, invisible structures, detectable only by their faint gamma-ray glow. What could have created these enormous bubbles? The signal is a ghost, an echo of a powerful event that happened millions of years ago. One possibility is that they are the remnant of a period of intense star formation. Near the galactic center, a starburst that blew a galactic superwind, inflating these giant lobes. Another more tantalizing possibility is that they are the signature of a massive eruption from our galaxy's central black hole, Sagittarius A. Perhaps millions of years ago, a star or a large cloud of gas fell into the black hole, triggering a massive release of energy that blasted these jets of plasma into the galactic halo. If so, our galaxy's heart was not always as quiet as it is today. It was once a quasar, a brilliant, violent beacon that lit up the entire Milky Way. The Fermi bubbles are a signal of our galaxy's turbulent past, a ghostly monument to a fire that has long since died down, leaving only a faint high-energy glow in its wake. While most stars in our galaxy drift in quiet, predictable orbits, a few are moving with an incredible, shocking speed. These are the hypervelocity stars, and they are moving so fast that they are escaping the gravity of the Milky Way entirely. They are a signal of a violent encounter at the heart of our galaxy. These stars are thought to be born in binary star systems. When such a system wanders too close to the supermassive black hole at the galactic center, the black hole's immense gravity can tear the binary pair apart in a gravitational slingshot. One star is captured into a tight orbit around the black hole, while the other is flung out into space at a speed of millions of miles per hour. These are the loneliest stars in the universe. They travel alone, unbound to any galaxy, destined to drift forever in the vast empty void between the galaxies. Each hypervelocity star is a signal, a message from a dramatic event we could not see. It is the surviving partner of a stellar dance that ended in tragedy at the edge of a black hole. By tracing their paths back, we can learn about the dynamics of the galactic center and the powerful unseen forces that govern it. As our radio telescopes have listened to the sky, they have detected the faint, ever-present glow of the cosmic microwave background, but they have also detected another more mysterious background signal, a faint hum of radio noise that seems to be coming from our own galaxy, but has no clear source. This is the galactic hum, or the synchrotron background. It is a diffuse glow of radio waves that is far stronger than our models predict. We know that cosmic rays spiraling in the galaxy's magnetic fields produce synchrotron radiation. But the observed hum is 6 times louder than all the known sources of cosmic rays and supernovae can account for. So, where is the extra signal coming from? Is it the blended glow of thousands of faint, undiscovered radio sources, like distant pulsars or star-forming regions? Is it a sign of a new population of cosmic ray electrons that we don't know about? Or could it be something more exotic, like the faint signal of dark matter particles annihilating in the galactic halo? For now, we don't know. The galactic hum is a quiet, persistent mystery. It is a signal that our own home galaxy is humming with a radio music, whose source we cannot find, a gentle, pervasive static that tells us we still have much to learn about the invisible processes that fill the space between our own familiar stars. From the natural, though often mysterious signals that fill the cosmos, we turn now to a search for a signal of a very different kind. A signal that is not born from a dying star or a spinning black hole, but from a thought. This is the search for extraterrestrial intelligence, or SETI, the quiet, patient act of listening for a message from another mind. For decades, we have pointed our radio telescopes at the stars, listening for a single, narrow-band artificial signal that would tell us we are not alone. And for decades, we have been met with a profound and deafening silence. But in 2019, a signal was detected that made the listeners hold their breath. It came from the direction of Proxima Centauri, the closest star to our Sun, a star that we know has at least one planet orbiting in its habitable zone. The signal was a narrow-band radio emission, just the kind of artificial signal that SETI researchers have been looking for. It was detected by the Parkes telescope in Australia during a period of observation for the Breakthrough Listen project. The signal was there, then it was gone. It appeared in several scans over the course of a few hours, and it seemed to be drifting in frequency in a way that would be consistent with a source on a moving planet. It was named Breakthrough Listen Candidate 1, or BLC-1. For a year, the team analyzed the signal in secret, trying to rule out every possible source of terrestrial interference. Could it be a satellite, a ground-based radio transmitter, a glitch in the equipment? The excitement was immense. This was the most compelling candidate signal since the WOW signal, and it was coming from our nearest stellar neighbor. But in the end, and after a year of painstaking work, the team concluded that the signal was almost certainly human-made interference. It was a radio signal from Earth that had bounced off something and been reflected into the telescope, mimicking the characteristics of a true extraterrestrial signal. It was a disappointment, but also a valuable lesson. The search for a whisper from the stars is incredibly difficult, and the universe is filled with the echoes of our own noisy civilization. While the big, well-funded SETI projects scan the sky, millions of people around the world have been contributing to the search from their own homes. This was the SETI at Home project, which ran from 1999 to 2020. It used the idle processing power of millions of personal computers to sift through the vast amounts of data collected by radio telescopes. Over its 20-year run, SETI at Home was one of the largest distributed computing projects in history. It analyzed data that would have taken a single supercomputer centuries to process. And while it never found a definitive signal of intelligent life, it did find several intriguing candidate signals. One of the most famous was SHG B02 Swarthine. It was a faint narrowband radio signal observed 3 times from the same point in the sky. Its frequency was about 1420 megahertz, the frequency of neutral hydrogen, a magic frequency that many have speculated would be a logical choice for interstellar communication. And it was drifting in frequency at a very rapid rate, a rate that would suggest it was coming from a planet rotating much, much faster than Earth. Was it a real signal? Or was it, like so many others, just a strange form of noise or a glitch in the detector? We don't know. The signal was too faint to be confirmed, and follow-up observations have found nothing. It remains a quiet, tantalizing what if, a single interesting point in a vast ocean of data discovered not by a professional astronomer, but by the combined silent work of millions of hopeful minds. The greatest and most profound signal in the search for extraterrestrial intelligence may not be a signal at all, but the lack of one. This is the Fermi paradox, or the Great Silence. Our galaxy is vast and ancient. It contains billions of stars older than our sun, and we now know that it is filled with billions of Earth-like planets. Given all of that time and all of those opportunities, it seems that life should be common, and that at least some of it should have evolved into intelligent technological civilizations. So where is everybody? Why, when we listen to the sky, do we hear only the natural, chaotic symphony of the cosmos and not the clear, artificial signals of intelligence? This silence is a signal in itself, and it is a deeply unsettling one. What does it mean? Are we truly alone in the galaxy? A singular, miraculous accident? Is intelligent life common? But does it inevitably destroy itself before it can reach for the stars? Or is the galaxy full of life? But are they all deliberately silent, hiding from some unknown danger? Or are they broadcasting in ways we cannot yet understand, using technologies far beyond our own? The Great Silence is a question that hangs over all of astronomy. It is the quiet, empty background against which we conduct our search. It is a signal of absence, a profound and unanswered question that speaks to our deepest hopes and our deepest fears about our place in the universe. The search for intelligent signals is not limited to radio waves. If a civilization wanted to send a message across the stars, it might choose to do so with light. This is the idea behind optical SETI. Instead of listening for radio broadcasts, these projects search for brief, powerful flashes of laser light. A laser beam can be tightly focused, and a powerful pulse could briefly outshine its host star, making it visible across interstellar distances. An advanced civilization could, in theory, use a powerful laser to send a pulsed message, a kind of cosmic Morse code written in flashes of light. We are searching for these signals with specialized telescopes that can monitor thousands of stars at once, looking for flashes that last for just a nanosecond. So far, we have found nothing that is unambiguously artificial. But the search is young. It is another way of listening, another way of asking the great quiet question. It is a reminder that a message could come in many forms. It might not be a steady broadcast, but a single, brilliant flash of light in the night, a signal that travels with the speed of light and the patience of eternity, waiting for someone to be looking at just the right moment. As our journey through the cosmic signals nears its end, we realize that the universe is speaking to us in 1,000 different languages. We have listened to its rhythms, its shouts, its murmurs, and its silences. But the oldest and most fundamental language of all is light itself. Every photon that travels from a distant star to our telescopes is a messenger, and encoded within that light is a story. When we pass the light from a star or a galaxy through a prism, it splits into a rainbow of colors, a spectrum. But this spectrum is not a smooth, continuous band of light. It is crossed by dark, thin lines. These are absorption lines, and they are the chemical fingerprints of the star. Each dark line corresponds to a specific wavelength of light that has been absorbed by a specific element in the star's atmosphere. By reading these lines, we can determine with incredible precision what the star is made of. We can see the signature of hydrogen, helium, carbon, iron, and dozens of other elements. We can measure the star's temperature, its pressure, its magnetic field, and even how fast it is rotating. The spectrum of a star is a signal of its very essence. It is a quiet, detailed message that tells us the story of the nuclear fire burning in its heart and the chemical soup that makes up its body. It is a language of light and shadow that allows us to understand the life of a star from a distance of 1 trillion miles. Just as a star's atmosphere can leave dark absorption lines in its spectrum, a glowing cloud of gas in space can create the opposite bright emission lines. When a cloud of hydrogen gas is energized by the light of nearby hot young stars, its electrons are kicked into higher energy states. As they fall back down, they emit light at very specific wavelengths, creating a spectrum of bright, colorful lines. These emission nebulae are the nurseries of the cosmos, the places where new stars are being born. Their light is a signal of creation. The beautiful, glowing colors we see in images from the Hubble Space Telescope are often color-coded representations of these emission lines. Red for hydrogen, green for oxygen, blue for sulfur. By studying these lines, we can map the chemical composition of these stellar nurseries, and we can see the raw materials from which the next generation of stars and planets will be formed. The signal is a quiet, radiant glow, the beautiful, life-giving light of a cosmic cradle. One of the most profound signals in the universe is not a presence, but an absence. It is a shadow. In 2019, the Event Horizon Telescope, a global network of radio telescopes all working together, captured the first direct image of a black hole's shadow. We cannot see the black hole itself. Its gravity is so strong that no light can escape, but we can see the brilliant swirling disk of hot gas that surrounds it. And in the center of that glowing ring, there is a perfect circle of darkness. This is the black hole's shadow. It is the region of space-time from which light can no longer escape the final one-way boundary of the event horizon. The size and shape of this shadow are a direct prediction of Einstein's theory of general relativity. And the image captured by the telescope matched the prediction perfectly. It is one of the most beautiful and powerful images in the history of science. It is a signal not of light, but of its absence. It is the silhouette of a gravitational monster, a quiet, dark circle that proves the existence of one of the most mysterious and enigmatic objects in the universe. It is a picture of the edge of reality itself. The universe can send signals not only directly, but also through echoes. When a star explodes as a supernova, it sends out a brilliant flash of light that travels outward in all directions. If there is a cloud of dust near the exploding star, this light will hit the dust and scatter, creating what is known as a light echo. The light that travels directly from the supernova to us arrives first. But the light that travels to the dust cloud and then scatters toward us arrives later because it has traveled a longer path. This means we can see the flash of the supernova, and then months or even years later, we can see the same flash of light sweeping across the nearby dust clouds, illuminating them like a cosmic searchlight. These light echoes are beautiful, expanding rings of light, but they are also a powerful scientific tool. They allow us to study the supernova from different angles, and they create a three-dimensional map of the dust clouds around the star. They are a signal from the past, an echo of a violent event that is long over, but whose light is still painting the clouds around it. It is a quiet, gentle reminder that even after a great fire has gone out, its light can continue to travel and to reveal the hidden structures of the darkness it passes through. And so our long, quiet journey through the signals of the cosmos comes to a gentle close. We have drifted from the first solitary shout of the wow signal to the steady cosmic heartbeats of pulsars. We have heard the violent roar of fast radio bursts and the faint space-time warping murmur of colliding black holes. We have listened to the chaotic flickering of quasars from the universe's youth, and we have seen the silent ghostly glow of the Fermi bubbles in our own galactic home. We have learned that the universe is not a silent place. It is a symphony of signals, some loud, some quiet, some rhythmic, some chaotic. It is a symphony that has been playing for 13 billion years, and we are only just now learning how to listen. Each signal is a note in this grand cosmic composition. Each one tells us a story of creation, of violence, of beauty, and of mystery. And perhaps the most profound signal of all is the one that is not out there in the darkness, but right here in the quiet space of your own awareness. The fact that you are here now thinking about these things is a signal in itself. You are a part of the universe that has woken up. You are a collection of stardust forged in the hearts of ancient stars that has somehow learned to look back at the stars and wonder. In this sense, you are not just a listener to the cosmic symphony. You are a part of it. You are a way for the universe to know itself. Your curiosity, your wonder, your sense of awe, these are signals too. They are the universe becoming aware of its own beauty, its own mystery, and its own vast silent grandeur. As you lie here now, letting these thoughts drift away, like fading starlight, feel the quiet connection between the vastness of the cosmos and the stillness within you. The same atoms, the same forces, the same ancient history connects them both. You are not separate from the universe. You are a living, breathing, dreaming piece of it. And now there is nothing left to do. No more signals to decipher, no more mysteries to solve. Just the calm, quiet rhythm of your own breath and the gentle, dark space of rest. Let the universe and all its wonders fade into the background. Let your body grow heavy and your mind grow still. The symphony will continue to play, but you can let it go. Your part for tonight is done. If you happen to still be awake, you can go ahead and let the next journey begin. But if sleep is close, simply let it come. Let it carry you into a silent, dream-filled space where there are no questions, only peace. Rest well. And thank you for listening to the universe with me. And so, our long listening has come to a quiet end. We have drifted through the static and the silence, hearing the whispers of dead stars and the ancient echoes of creation. We have felt the universe speak to us, not in words, but in rhythm, in light, and in the gentle, patient language of gravity. And now, as the echoes of these cosmic signals begin to soften in your mind, we can let ourselves wonder, very gently, what they might mean for us here in our own small, quiet lives. For what is the purpose of listening to the universe, if not to better understand how to live within it? The first and perhaps most beautiful lesson these signals offer us is the art of listening itself. In a world so full of noise, a world that demands our constant attention and immediate response, the universe teaches us a different way. It does not shout for our attention. Its most profound messages, the steady pulse of a distant pulsar, the slow decay of a binary orbit, the faint ancient glow of the cosmic background are whispers. They are signals that can only be heard with immense patience, with stillness, and with a willingness to listen for what is quiet and subtle. And so it is in our own lives. The most important truths are rarely found in the loudest voices or the most urgent demands. They are found in the quiet spaces between words, in the gentle, unspoken cues of a loved one, in the faint inner whisper of our own intuition. We spend so much of our lives talking, planning, and doing that we forget how to simply listen. But the cosmos reminds us that listening is not a passive act. It is a form of deep engagement, a way of opening ourselves to the world and allowing its stories to unfold at their own pace. Perhaps, then the first lesson we can carry into our sleep is a gentle invitation to listen more deeply to the world, to each other, and to the quiet, steady truths that are always there, waiting patiently to be heard. These signals also teach us about the profound beauty of silence. We encountered the great silence of the Fermi paradox, the vast empty expanse of the Buddha's void, and the perfect dark shadow of a black hole. In our world, silence can feel uncomfortable, like an emptiness that needs to be filled. But the universe shows us that absence can be as meaningful as presence. The great silence is not an empty void. It is a question that invites us to ponder our own significance. The cosmic voids are not just nothingness. They are the structures that give shape to the glowing filaments of the cosmic web. The shadow of a black hole is not just darkness. It is the only way we can see the brilliant ring of light that surrounds it. In our own lives, too, there is a deep and nourishing power in the silences. The pause in a piece of music that gives the notes their meaning. The quiet stillness of a morning before the world wakes up. The comfortable silence between old friends that speaks more than words ever could. We often run from these moments, filling them with distractions and noise. But perhaps as we drift toward sleep, we can learn to embrace them. We can learn to see silence, not as an emptiness to be feared, but as a space for rest, for reflection, and for peace. A quiet, gentle space where our own thoughts have room to breathe and our own hearts have a chance to be still. And as we find these connections, it's worth remembering very softly that the stories and lessons we weave from these cosmic signals are here for reflection, for wonder, and for educational purposes alone. They are gentle invitations to see our own lives through a wider, more peaceful lens. The journey of these signals across billions of years teaches us a lesson in patience. The light from a distant quasar began its journey long before our Earth was even formed. The gravitational waves from two colliding black holes traveled for 1 billion years before their faint chirp reached our detectors. The universe does not hurry. It unfolds in immense, unhurried arcs of time. And yet we in our short lives often live in a state of constant urgency, feeling that everything must happen now. We grow impatient with our progress, with our healing, with the slow, unfolding story of our own lives. But the stars and their signals offer a different perspective. They remind us that true growth, true change, happens slowly over time. Like a river carving a canyon, or a galaxy slowly spiraling into a new form, the most profound transformations are often the most gradual. So if there is something in your life that feels stuck, or a goal that feels impossibly far away, perhaps you can take comfort in the patient rhythm of the cosmos. Trust in the slow work of time. Allow things to unfold in their own season. The universe is in no rush, and neither tonight are you. Perhaps the most comforting lesson of all comes from the mysteries themselves. Again and again on our journey, we came to the edge of what we know and found ourselves saying, "We don't know." We don't know what dark matter is. We don't know why the universe is accelerating. We don't know if we are alone. In a world that values certainty and quick answers, this can feel like a failure. But in the quiet contemplation of the cosmos, the unknown is not a void to be feared. It is a space of wonder. It is the unknown that keeps us curious, that keeps us searching, that keeps us humble. To embrace the mystery is to let go of the need to have everything figured out. It is to accept that life is a journey of discovery, not a puzzle with a single right answer. And this is a profound gift. It means you do not need to have all the answers for your own life. It is okay to be uncertain. It is okay to be in the middle of a story you do not yet understand. Like the astronomers who listen patiently to the sky, you can simply be present with the questions and find a quiet peace in the wonder of it all. And finally, these signals from the gravitational waves that connect colliding stars to the cosmic web that links all galaxies tell us that nothing is truly alone. Everything is connected. Every atom in your body was forged in the heart of a star that died billions of years ago. The light that you see from a distant galaxy is a part of its story that has become a part of yours. We are all, in the most literal sense, made of starlight, and we are all held in the same invisible web of gravity and space-time. This deep, cosmic connection extends to us here. It reminds us that our own small actions, our own quiet moments of kindness or compassion ripple outward in ways we may never see. We are not isolated islands, but part of a single, vast, interconnected whole. And there is a deep and abiding peace in that knowledge. It means you are a part of something immense, beautiful, and eternal. You belong to the universe, and the universe belongs to you. So now, let these thoughts soften. Let them dissolve like clouds in the night sky. There is nothing left to solve, nothing left to hold on to. Just the quiet darkness and the gentle, steady rhythm of your own breath. You have listened to the universe, and now it is time to rest. You are a part of its story, a part of its song, and for tonight, your note is one of peace and of stillness. Sleep well and dream softly. Good night.